Hello and welcome everyone to the second lecture of this course, and today we will be discussing some fundamentals of solar radiation, starting with understanding the sun and some fundamentals of blackbody radiation. So this schematic figure here, as you can see, represents a very simple schematic of the sun. So as we understand, in the core of the sun we have nuclear fusion reactions happening. And these fusion reaction which is happening at the core of the sun, that converts hydrogen into helium, and it happens at a very high pressure and temperature. So the temperatures in the core of the sun can be as high as up to 20 million Kelvin. So that's a very high temperature. We can't even imagine that being on the planet Earth. But interestingly, from the core to the surface of the sun, there are some other phenomena which come into place. So after the core, there is one layer of hydrogen ions which absorb the sun's radiation from the core. So this absorption by hydrogen ions, as you can see here, there is a red colored semicircle here in the figure. So that represents those hydrogen ions and absorption by hydrogen ions. So due to the absorption of radiation by the hydrogen ions, the temperature towards the surface of the sun is drastically reduced. And the main phenomena of heat transfer from the core of the sun to the surface of the sun is through convection. So as you can see in the outer orange layer here, there is convective heat transfer happening. So convective heat transfer is the major phenomena for transferring heat from the core of the sun towards its outer surface. And finally, we have the sun's outer surface, what we call as the photosphere. So photosphere is the outermost layer of the sun, and this is what is visible to us from the naked eye when we look at the sun from Earth. So the temperature of the photosphere is somewhere around 6000 Kelvin, which is drastically less than the core, but still several times higher than what we as humans have in our experience. So that is a little bit of understanding of the sun. Why that is important? Let's look at it. So most of the sources which emit radiation, they are modeled as black body radiation sources. So when we say a black body, what do we mean by a black body? So when you're saying a black body, basically what it means is that it absorbs all the radiation which is incident on its surface, and it emits radiation only based on its temperature. So the black body emits radiation which depends on the temperature of the black body. And by definition, as we know, black body absorbs all the radiation incident on it. So there is no reflection which is happening from the surface of the black body. So the entire radiation or the entire spectrum which is coming from the surface of a black body is solely dependent on its temperature. And that is why it's important to look at the temperature of the sun at the photosphere. So the spectrum of the sun which we receive at any place in the solar system, be at the planet Earth or any hypothetical place in the solar system, whatever spectrum of solar radiation is received, that depends upon what is the temperature of the photosphere. So here in this figure, as you saw, we said it is 6000 Kelvin. That is sort of a very crude approximation. There are different other estimates of the radiation of the temperature of the photosphere. So there are different estimates. Sometimes some of the literature, it talks about that this photosphere has a temperature of 5762 Kelvin plus minus 50 Kelvin. Some other literature also talks about that this temperature is being considered as 5730 plus minus 90 Kelvin. And when you look at the field of astronomy, so the astronomers, they characterize the sun as a star which has a surface temperature of 5778 Kelvin. So that way there are all these numbers, as you can see, they are very much in the same range, around the same close proximity, but different estimates, different studies, different models, they give different numbers in the same range. So if we want to sort of characterize the spectrum of the sun, we need to zero down on a particular value, and there is some, as we can see, there is some sort of variation in different studies and estimates. So in this course, we will consider the temperature of the sun, T sun, or the photosphere temperature as 5800 Kelvin, which is very near to all these different estimates which we see here. And it gives a sort of a good trade off between complexity and accuracy. So it's quite simple, a simple and straightforward number rounded off to the closest 100, and gives quite accurate results. So for this course, we will be considering sun as a black body having temperature at 5800 Kelvin, and accordingly its spectrum we will consider. So when we talk about a black body, one thing is that we talked about the temperature of the black body, which gives the spectrum of the black body. Now there are different physical laws which govern the behavior of a black body and how the radiation from a black body behaves. So one very important physical law in this context is known as the Planck's radiation law. Planck's radiation law gives us the spectral irradiance from a black body, and it is given by this particular equation. The spectral irradiance F at a given wavelength lambda is given by this equation, 2 pi hc square divided by lambda to the power 5 into e to the power hc by k lambda t minus 1. So this Planck's radiation law, it gives us the spectral irradiance of a black body. And in this equation, if we look at it little more detail, so this F is what we call as the spectral irradiance. And the spectral irradiance, typically it is measured in the units of watt per meter square per micrometer. So as we understand, when we talk about irradiance, it is basically a power density. So how much power is being emitted by a unit area. So watt per meter square is the irradiance, but then here we are linking it with the wavelength. So at a given wavelength, what is the intensity of emitted radiation? That is why watt per meter square per micrometer. So that is the spectral irradiance. Lambda in this equation, as we just now looked at, that is the wavelength of light under consideration, which can be in micrometers. And then you have the temperature of the black body, which is in the Kelvin. So you have T is the temperature of black body in consideration with the unit of Kelvin. And the other three entities in this particular equation, H is the Planck's constant, C is the speed of light in vacuum, and K is Boltzmann constant. So using this particular equation, we can find out that what is the intensity of radiation which is being emitted by a black body at a given wavelength, where the black body is at temperature T. So as you can see, in this equation, the only two variables are lambda and T. T is the temperature at which the black body is presently existing, and lambda is the wavelength at which we are estimating the spectral irradiation. The other three variables, other three alphabets here, H, C and K, they are nothing but constants. So they will be just constant in the equation. So in this equation, T is the main determining factor. So how much spectral intensity will be there at a particular wavelength is nothing but dependent on the temperature of the black body. Now this equation looks quite complicated. Now if I were to ask you that estimate the radiation intensity at each wavelength, then it might seem quite cumbersome to you, especially given that there are so many wavelengths. If you look at the entire electromagnetic spectrum, so you have ultraviolet region, you have visible region, infrared region. So there is a huge gamut of wavelengths. And if I were to solve this equation at each wavelength and find out the spectral irradiation, it would be a very cumbersome task. But thankfully for us, someone else has done the difficult task for us. So let's look at that very interesting result. So if I were to estimate the total radiation intensity or the total power density emitted by a black body, I can say, let's say that H is the total power density, emitted by a black body. So this H will be nothing but integration from 0 to infinity f lambda d lambda. So f of lambda is the same spectral irradiation function which we saw in the previous slide, and this f lambda or the spectral irradiance, if we integrate across all the wavelengths, 0 to infinity, then we will get the total power density or H. Now again, if I were to ask you to integrate that particular equation where you have lambda to the power 5 and then also multiplied by some exponent having a function of lambda, that again is not such a very straightforward task. It might seem quite cumbersome to integrate it over the entire wavelength region. But the interesting thing is that this result has also been solved, and we have one very simple and very condensed form of this result, which is very well known and widely used in several disciplines of physics. And this is this Stephen-Boltzmann law. You have H equal to sigma T to the power 4. So here H is the total power density, T is the temperature of the black body, and sigma, that is known as the Stephen-Boltzmann constant. So thankfully scientists have already worked on this and need not rack our brains too much with those cumbersome equations of a spectral irradiation. We can directly use this H equal to sigma T to the power 4, this simple equation, for estimating the power density of any black body. Now let's do a quick numerical. So suppose if I were to ask you to estimate the surface luminosity of the sun. So as we can see, the surface luminosity of the sun or the overall power density of the sun, we can directly use this Stephen-Boltzmann equation for finding that out. And we know that sigma here, the Stephen-Boltzmann constant, is a well known constant. It is 5.67 into 10 to the power minus 8 watt per meter square k to the power 4. So that is the value of sigma. The temperature of the sun, as we just now discussed a few minutes ago, will be taking simple approximation of the temperature of the sun or the temperature of photosphere as 5800 Kelvin. So if I use this value of temperature of sun and sigma at that particular value, and we substitute these two numbers in the equation H equal to sigma T to the power 4, then what we'll get is that H sun or the surface luminosity of the sun is 64.17 megawatt per meter square. So that is one important result. So this is the amount of power which is being emitted every second by sun. So each meter square, each unit area, 1 meter square area of sun is emitting roughly around 64 megawatt of power. Now that's a huge amount of power. And just to put it in context, we would like to see how does it translate into the total power emitted by the sun. So if we want to estimate the total power emitted by the sun, so we will approximate sun with a sphere, which is sort of a fair degree of approximation, and let's say this radius of the sun is r sun. Now for a sphere, we know that the total surface area is equal to nothing but 4 pi r square, and the radius of sun, as has been estimated by astronomers, is around 695 million meters. So 695 into 10 to the power 6 meters. the H sun or the radiation intensity at the surface of the sun, surface luminosity of the sun, that we just now found out, that is 64.17 into 10 to power 6 watt per meter square. So using this value of radius of sun, if we estimate the total surface area of sun, that will be equal to 4 pi into square of radius of sun, and that number comes out to be around 6.07 into 10 to power 18 square meter. So this is the total surface area of sun, and we have already found out the surface luminosity. So we know that 1 meter square of area of sun, surface area of sun, that emits around 64 megawatt of power. So if I want the total power output of sun, it will be nothing but this surface luminosity multiplied by the surface area of sun, and these two numbers, if we multiply them together, what we get is the result is somewhere around 3.9 into 10 to power 26 watts. So that is the amount of power being emitted by the sun at each instant, at every second, 3.9 into 10 to power 26. Now that's a very huge number. 10 to power 26, that means you will have 39 followed by 25 zeros if you were to write that number fully. So that's a huge number. And just to put it in context, what is the total power requirement of planet Earth, of all the human beings, for all the human activities on planet Earth? What is the total power requirement? So again, there are different estimates, but usually the consensus somewhere around, if you look at the total power demand of planet Earth, then that is roughly of the order of around 16 terawatts. So terawatt is 10 to power 12 watts, and you see here the power emitted by sun is of the order of 10 to power 26 watts. So that is like a million billion times higher than what is the total power requirement of this planet Earth. And no doubt sun is the basis of all energy on planet Earth, and as we discussed in the first lecture, all the different forms of energy sources that can be traced back to the sun. One additional result in this context, when we talk about the black body radiation and the radiation emitted by sun, another interesting result is what is the nature of the spectrum, at what particular wavelength does the solar spectrum peak. So again, I mean, if we were to refer to the spectral irradiance equation f of lambda, which we looked at a few minutes ago, if I were to find out what is the wavelength at which the peak solar radiation is happening, then one very simple way of doing that would be that we differentiate the equation of f lambda with respect to lambda. So d f lambda by d lambda, and we equate it to equal to 0. And if we solve this equation, we will get the value of lambda at which the peak radiation intensity is happening. So again, this has been done by another particular scientist known as Wien. So we have one very famous result here also, which is known as the Wien's law. And Wien's law tells that what is the wavelength at which a particular black body has its peak spectral irradiation. So this wavelength where the spectral irradiation is peaking, that we indicate by the symbol lambda p, and if I were to write in micrometers, then this I can simply write it as 2900 by T, where T is the temperature of the black body. So again, this is a very simplified equation, but very useful one in this context. So here lambda p is the wavelength where peak spectral irradiance is obtained, and T is the temperature of the black body. So that's a very interesting result. And now probably you can appreciate why a few minutes back I was saying that we are approximating the temperature of sun as 5800 Kelvin, especially due to this equation. So 5800 Kelvin, as you can see, if you put that value here, very simply you will get that the lambda p for sun, the peak spectral irradiation of the sun happens at a wavelength of around 0.5 micrometers. And that is a characteristic of the solar spectrum. And if you were to recall the basics of electromagnetism and where that wavelength would lie, so it lies in the visible region of the spectrum and specifically around the green color. So when we have the spectrum of the sun, there is ultraviolet, infrared and visible regions. In the visible region, almost in the middle, you have the green color, and that is where the spectrum of the sun peaks. And this we can look at it with this particular figure. So the solar radiation has this type of a profile. So the green curve here which you see, that is representing the spectral irradiation of the sun, the spectrum, the nature of the spectrum of the sun. So on the y axis you have the sunlight intensity, and on the x axis you have the different wavelengths from ultraviolet to visible to infrared region. And in this entire spectrum of electromagnetic radiation, you can see there is this visible region here starting from somewhere around 0.35 micrometer going up to around 0.75 micrometers. And in that visible region, the value at which the radiation is peaking is at 0.5 micrometer here. So as you can see, that is where the spectral intensity for sun peaks. So that is also one important and interesting result related to the spectrum of the sun and the way the sun behaves as a black body source. So we looked at the behavior of the sun in terms of what is the temperature of its photosphere, how it behaves as a black body radiation source, and what is the surface luminosity of the sun, what is the total power emitted by the sun, and also the nature of the solar spectrum in terms of the wavelength at which it peaks. But now, as we understand, sun is at a very far distance away from planet Earth, and as the radiation will have to travel a longer distance, what will happen is that the radiation which was emitted by the solar disk, as it travels over longer distance, then the same radiation has to cover a much larger surface area. So just to explain that concept, let's say if you have the solar disk here, the sun I am representing here, and there is some surface luminosity of the sun which we just now estimated, 64 megawatt per meter square. But now if I were to go some d distance apart from the sun, d distance away from the sun, now at this d distance I will need to draw a hypothetical sphere, something of that sort, and now this spectral irradiation or the total power intensity which was being emitted by the solar disk, that same intensity, that same amount of power is spread across this larger sphere whose radius is d. So what it means, the total power emitted is same, but now it is spread over a much larger surface area. So what it would imply is that at a given point the intensity of radiation would be lesser, and that is the reason as you go farther away from the sun in the solar system, then the solar intensity or the solar radiation intensity goes on decreasing. So let us try to quantify this particular thing also. So to quantify this, let us look at this very simple schematic. So suppose we have the sun disk here, and the radius of the sun is given here as r, and there is a radiation intensity or the surface luminosity of the sun which is just at the photosphere, at the surface of the sun, this is given as h sun. And now we want to estimate what would be the radiation intensity at a distance d apart. So in this figure, as you can see, we have indicated that as h naught. So if we go step by step on this, so the total power emitted by the sun is nothing but H sun, which is the surface luminosity of the sun, multiplied by the surface area of sun, which is 4 pi r square. So, that is the total power emitted by the sun. Now, the same power travels over a longer distance. So, at a distance d apart, let us say we have a hypothetical sphere with a radius of d. So, the surface area of that sphere, total surface area would be 4 pi d square. So, if we were to estimate what will be the radiation intensity or the power density at that distance d apart, then we can say that the radiation intensity at distance d from the sun would be nothing but the total power emitted by sun, H sun, multiplied by 4 pi r square, divided by the surface area of the hypothetical sphere at distance d. So, which is nothing but 4 pi d square. And as you can see here, 4 pi and 4 pi gets cancelled. This simplifies into this equation, H sun multiplied by r by d whole square, where r is the radius of the sun and d is the distance from the sun at which we are interested in estimating the solar radiation intensity. So, this is again a very useful result. This gives us the radiation intensity at any distance d from the sun. So, we can use this result to estimate what would be the surface radiation intensity at any of the planets in the solar system. So, let us do one simple and interesting exercise to do that estimation. So, let us look at the planets in the solar system and what is their distance, how much distance apart they are from the sun, and accordingly how much would be the mean solar irradiation at the surface of different planets. So, let us make a small table to put those results here. So, first column we are putting the name of the planet and then the distance, how much is the distance between the sun and that particular planet, and that we are putting in billions of meters. So, 10 to power 9 meters, and accordingly what would be the mean solar irradiance in watt per meter square at the surface of that particular planet. So, first one, Mercury, that is at a distance of roughly around 57 into 10 to power 9 meters from the sun, and we use our same equation which we just now looked at. So, your H naught is nothing but H sun multiplied by r square divided by d square, whereas we just now saw H sun is nothing but 64 into 10 to power 6 watt per meter square. R or radius of sun is 695 into 10 to power 6 meters, and d for Mercury is 57 into 10 to power 9 meters, and if you put it in the equation and solve it, you get something around 9514 watt per meter square. So, that is a radiation intensity at the mean distance between sun and Mercury. Next planet, if you go to Venus, Venus is at a distance of 108 into 10 to the power 9 meters from the sun approximately, and the mean solar irradiation intensity at that particular distance using this concept would come out to be around 2650 watt per meter square, again several times higher than what we have on Earth. Next one, Earth. Earth is at around a mean distance of 150 billion meters from the sun, and at that distance with this formula we come out to around 1374 watt per meter square. Next one is Mars. Mars is at a distance of 227 billion meters, and the radiation intensity comes out to around 600 watt per meter square. Then you have Jupiter at a distance of 778 billion meters. Radiation intensity is around 51 watt per meter square. Saturn at a distance of 1426 billion meters, radiation intensity comes out around 15 watt per meter square. Uranus at a distance of 2868 billion meters, and the radiation intensity is hardly around 3.8 watt per meter square. And then we have Neptune at a distance of 4497 billion meters, and the radiation intensity is hardly 1.5 watt per meter square. So that is the situation of different planets in the solar system. We at Earth are situated here, 1374 watt per meter square, but please mind that this is the mean solar radiation at the Earth Sun distance. We have still not taken into account the atmospheric effects. So without considering the effect of atmosphere, just at the mean distance between the Sun and the Earth, the radiation intensity would be around 1370 watt per meter square. The closest neighbor to us is Mars, and Mars also, as you can see, is in that zone around the radiation intensity of Earth, whereas all the other planets, the other two which are further closer to Sun than us, Mercury and Venus, they are having a very high radiation intensity, not possible for life to thrive on them. And others beyond Mars, they have a very low radiation intensity. Again, as we understand life in its form at Earth, not really suitable radiation intensity for life to flourish. Whereas Mars is almost in a comparable zone around Earth, and probably that's the reason why some people are interested in finding out if there is life on Mars as we understand. So that is it in this lecture. In the next lecture, we will look at what happens inside the Earth's atmosphere, and this radiation intensity which we found at the mean Earth-Sun distance, how that changes once we enter into the atmosphere and take the atmospheric effects into account. So that is it for this lecture. See you in the next lecture. Thank you.